is strengthening mechanisms, and we had looked at the mechanisms working for the strain hardening, mechanism for the grain size effect. That is, if I have a fine grain material, it's more difficult to make the plastic deformation go on. The yield strength of the material becomes higher, and it's a coarse grain material, yield strength is lower. Also seen the effect of the solutes, and we said that martensite is one wonderful structure which provides all the three mechanisms working. Fourth mechanism also works, which we are going to discuss today in martensite, that we have seen as secondary hardening. During tempering, if a carbide which forms is a very fine precipitate, it gives rise to secondary hardening. Why I need a fine precipitate? That we shall understand today when we talk about the precipitation hardening or edge hardening in materials. When the precipitate particles are present in the matrix all over the volume, they form an interface with the matrix. And that interface has an interfacial energy. Interfacial energy could be small, interfacial energy could be large, depending upon what is the precipitate and what is the matrix. Now, a dislocation which is moving, that is slipping in the matrix to cause the plastic deformation, has two options. It goes across the precipitate and cuts it through, or it bypasses the precipitate. What are these two mechanisms? We shall look at. Cutting through the precipitate is possible generally if the precipitate is very small in size, so that whatever the difference at the interface is, it provides, even with some strain, continuity of slip planes from the matrix to the precipitate. The precipitate is a different structure altogether. It can provide a continuity of the slip plane if it is small in size, like 10 angstrom, 20 angstrom. And depending upon the interfacial energy, pulse size is to be also restricted by that. If a high interfacial energy is there, size has to be very small, which can be cut. So that means the strains at the interface are going to be high. And if the interfacial energy is small, strains are going to be small. Small strains mean more matching planes. So that is what is happening. We'll show you that. And then if the precipitate becomes big enough, interface becomes incoherent. That is, doesn't provide me a continuity of slip plane. This location cannot enter the precipitate. So it has no alternative but to bypass it. How does it bypass this? That we shall see today. This is the cutting through mechanisms. Let's see, I have a, let us say, a dislocation here. A dislocation which is an edge dislocation, a positive edge dislocation, let us say. And with the applied stress, it is slipping in this direction. Well, suppose this provides a continuous slip plane which I have shown here. Maybe some strain there at the interface. So dislocation will continue to move as if there is no precipitate there. When it continues to move as if there is no precipitate, what happens is when it comes out onto the other side, like this, it cuts through the precipitate particle like this. Why does it do that? You have to recall how the dislocation slips. When this dislocation slips, by one step, it forms a plane this plane, actually it was a path plane, shifted to the left. And that is what is happening. All these planes are shifted by one step. One interplanar spacing, they are shifted to the left on the top. Bottoms have gone to the right. If it was a negative dislocation, it would be the other way around. So when the dislocation goes across the precipitate, it cuts through. That's why I call cutting through mechanism. Okay.
So what is the requirement for this?
Let's see. We will understand the mechanism. Well, let me go ahead for another. Not necessarily. It will cut differently. Depends what location it is. It can cut it through. Suppose that the dislocation is on this slip plane here. It can cut through here.
The precipitate should be of same size or something like matrix or.
No, it's not. It's just small enough. It means a different crystalline arrangement than that crystalline arrangement outside. But with some strain, it provides a continuity of the slip plane. Alright? That's because it's small in size, 10 to 20 angstrom outside the kind of diameter I'm talking about. It's a very small size. Now what has happened is when the dislocation, let's say I'm showing the two precipitate particles, the dislocation is here. This is the front. Let's say if I'm seeing in that direction, now I see it from the top view. That's from that direction. If I see in this direction here, that's the direction in which I view, then it looks like this. This is a dislocation line. These are the two precipitate particles. When it cuts through them, the top has gone to the left and bottom has gone to the right. As a result, just see carefully, this crescent area is an interface between the matrix and the precipitate, which did not exist before. Similarly, this crescent here is an interface between the matrix and the precipitate. This did not exist before, which is shown here, this part and that part there. Interface, additional interface area, additional interfacial energy. So when the dislocation was here, that extra interface was not present. When the dislocation has come out on the side, this interfacial area has come out. Thereby more interfacial energy is there. That energy should come from where? It should come from the person who is making the dislocation move, the one who is applying the resolved shear stress. So the resolved shear stress has to be increased in order to do this work, so that this energy gets stored here. So I have higher stress required to make the dislocation go across rather than the stress required to make it slip in the matrix. Here I don't have to apply that additional stress, but when I go across, I have to apply the high stress. Okay? And that additional stress which I need is increase in strength. Alright. That's one, and that is true when the interfacial energies are small, usually. When interfacial energies become too high, normally I have a lot of strain and I do not get any continuity of the slip plane. By that time, probably the precipitate has become much bigger. It contains, instead of some 50 or 100 atoms, it contains now 500,000 atoms. It has become much bigger in size, right? If that has happened, then it's possible for the dislocations to move still and cause the plastic deformation by bypassing the precipitate particle. We shall look at this process of bypassing. Let's say this is again a dislocation line. T vector and the B vector, I consider the same positive as dislocation. This dislocation gets obstructed when it comes near the interface of the precipitate and the matrix. So it starts to get pinned down here and starts going about the precipitate particle like this. But when it goes, the pinning points change. Pinning points keep changing, and till I reach the pinning point which is right here. And then this location is pinned at between these points, and you are trying to pull it. It forms a semicircle for which you have to apply the maximum possible stress. Like the Faircrete source, after that the further movement is automatic. So stress you need to apply here, if this is the distance between two precipitate particles, it's not a center to center distance, it's from surface to surface. Let's call it L. Then the stress I need to apply is mu b by L. Once it becomes a semicircle, it automatically goes to the other contours. And when it comes here, you can have your dislocation line vector going like this. In this position, dislocation vector T vector is here, here the dislocation vector is there, and therefore the opposite dislocations on the same slip plane. They come closer and cancel each other and form a loop like this. And the remaining part jumps like that. It jumps out, and the dislocation has come out with the same sign, same character, it comes out, but it has left behind a loop. Right? So that's called the bypassing the precipitate particle. This is how a dislocation can bypass the precipitate particles and still slip in. And the stress you need to apply is mu b by L. For this to be an effective strengthening mechanism, this L should be as small as possible. And that is what we discussed while talking about the precipitation hardening. As the time progresses, nucleation of more and more precipitate particles is taking place in the matrix, and thereby the interparticle spacing is decreasing. Since the interparticle spacing is decreasing, the strength is going up and up and up. However, it reaches an optimum value, that is when all the precipitate which is supposed to be formed as given by the lever rule is formed, and no more transformation is possible. Then the interfacial energy of the precipitate with the matrix is too high in such a situation, and then becomes a driving force for the next step, that is called the overaging or the coarsening of the precipitate. Precipitate begins to coarsen, thereby some precipitate particles dissolve in the matrix and they precipitate over the growing precipitate particles. So they grow in size, and therefore interparticle spacing begins to increase, the strength begins to decrease. That's why we also call it age hardening. As the time passes, the strength of the material initially increases. Once it reaches the optimum, it begins to decrease. Aging process is this, that precipitate process or precipitation process is on. It goes to completion near the optimum, and after that it begins to coarsen. Precipitate particles begin to coarsen and they become bigger in size. Right, so that's what we have seen, the stress required to bypass the precipitate particle. Mu is the shear modulus, B is the magnitude of the Burgers vector, and L is the space or the distance between the two precipitate particles, between which the dislocation has to go. And for that you need to apply this stress, which we also saw for Faircrete source, but I have not derived it, but this is what you take for granted in this course. But it is the stress which we need to apply. And from this it will be possible for us to see, while working some numbers in a problem, that length L should be in the range of few hundred angstrom. If it is more than that's 1000 or more, then it is not an effective strengthening mechanism. Certainly by the time it is 10,000, it has no effect. So I am looking for the size between 100 to 100 angstrom precipitate per diameter, and that shall be very So therefore, while talking about the precipitation transformation, I said the necessary condition is to obtain first the supersaturated solid solution, so that with time it goes to saturated solid solution and a precipitate form, the second phase forms. The sufficient condition I left at that time, and the sufficient condition now is the interparticle spacing, not center to center distance. Interparticle spacing should be submicroscopic in size, that's in the range of 100 to 200 angstrom to be effectively strengthening it. After maybe this is the kind of distance I get at about the optimum aging, but less than optimum aging it will be slightly more than this because fewer particles are present. Okay, so that's the kind of distances and spacings which we require for hardening to take place by precipitation, though such a situation of getting a supersaturated solid solution is present in almost all phase diagrams. But I do not get, say for example, most all diagrams show the decreasing solubility with decreasing temperature. Therefore, it should be possible for me to have a solid solution here and quench it to get supersaturated solid solution. But all alloys do not show me the precipitation hardening or the age hardening. There is a necessary condition, alright. I can quench it to keep it in solution, all the solute, but the precipitate forms does not provide me the fine interparticle spacing, what I am looking for in the range of 100 to 200 angstrom. Sufficient condition is not satisfied. That's why we took the example of aluminum copper alloy, which we call dualamine. Some non-ferrous alloys are producing this kind of precipitation hardening, and the aluminum is less strong as compared to steel, but you can get effective strengthening. And as a matter of fact, aluminum usually will be of the order of 100 megapascal strength. It can be made to go to 550 megapascal with alloying and giving rise to precipitation hardening. 5-fold increase in strength is possible. Right? That's the kind of thing which we get by precipitation hardening and some aluminum alloys. Alright, with this strengthening mechanism, and as I said, when we have alloying additions like vanadium, niobium, titanium, or tungsten, molybdenum, things like that, which produce very fine carbides during tempering, can give rise to secondary hardening in steels. That is also the same mechanism as the precipitation hardening. We shall look at the next deformation, which is a permanent deformation in materials, but this permanent deformation goes on as a function of time. What I call the viscous flow of the material or the creep. Okay? Creep, as I always said, is a permanent deformation, and it proceeds as a function of time, and I am not changing the applied stress. Stress is a constant. And it is a kind of a problem for engineers who are working in power plants. Let's talk about a turbine. Turbine is functioning normally at high temperatures, and it's working constantly for years together. The material is at high temperature and there is a stress all the time. It's rotating. In rotation, the blades go through the stresses. stress cycles, and it's all the time under stress, and it is at a high temperature. The creep can take place, blade can deform plastically, and if the blade increases by even a fraction of a millimeter, which crosses the clearance which you have between the casing and the blade, it will get jammed. The moment it gets jammed, it will break because there is a force acting already to make it move. And breaking of the blades is a very common problem in turbines. Right? So that's a creep taking place in such a place, location where the temperature is high, and this phenomenon is observed whenever the temperature exceeds 40% of the melting point. And the melting point is expressed in Kelvin. Okay? That shows that this phenomenon is a thermally activated process. Creep is a thermally activated process. We have seen that when plastic deformation occurs in a material, by and large it is the slip motion of the dislocation. Dislocation slip and cause plastic deformation in the material. And when that happens, more dislocations form because there are dislocation sources, and they start interfering with the moving dislocation. Work hardening or the strain hardening takes place. Now what is this thermal energy is doing? It is probably allowing this obstructive dislocation to overcome this obstruction. And I call the dislocation is getting relaxed. So I refer to this as relaxation mechanisms. While there is already strain hardening taking place when the plastic deformation occurs. Therefore, these are the two which are working opposite to each other. Once this hardening can be overcome with the cause of the relaxation, dislocation will continue to slip and deformation will go on. Okay? We shall try to look at these relaxation mechanisms in materials. Before that, we shall look at the phenomena logically what happens when the creep occurs in a material. This is the observation. On this axis I have the strain, on this axis I have the time. Time extends in years, so we can use the logarithmic scale. Well, these I have shown the three different curves. You can consider them at three different levels of stresses. Let us say sigma 1, sigma 2 and sigma 3. And I would say that sigma 3 is greater than sigma 2 is greater than sigma 1. You could also consider that same level of stress sigma but different temperature. Then this can also be the effect of T1, T2 and T3. And what we have is T3 is greater than T2 is greater than T1. Alright, on this axis, if you look at when the load is applied and the temperature is greater than the 40% of the melting point, instantaneously you get the deformation in the material, what is called the time independent deformation. Time independent deformation could be elastic, it could be elastic and plastic, depending upon what is the stress you have applied, what is the load value you have applied. And with that, once you load it, as a function of time, the strain keeps on, elongation keeps on going on, like goes on. Well, there are three parts of the curve which can be seen very clearly in the second one. First one here, second one there, and third one there. This is called the first stage, this is called the second stage, and this is called the third stage. I am differentiating these three stages on the basis of the slope of the curve. In the first stage, slope of the curve is decreasing with increasing time. In the second stage, the slope of the curve is constant. It's a straight line. In the third stage, the slope of the curve increases with increasing time. So I have the minimum strain rate, which is called a minimum creep rate, in the second stage. In the first stage, I have a creep rate higher than that. Creep rate is nothing but the slope of the curve, which is called the strain rate, because the strain and slope will be the derivative of the strain versus time, which is d epsilon 1 dt, is written like epsilon dot, which is called the strain rate. This strain rate is minimum in the second stage. In the first stage, initially the slope is high and it continuously keeps on decreasing, right? And the second stage is also called the steady state because the strain rate or the creep rate is a constant. It keeps on flowing at the same rate. And the third stage or the tertiary stage, creep rate increases with increasing time. There are different things that are happening in the three stages. In the first stage, obviously there are two things which I said which are working. One is the strain hardening, other is the relaxation. Which one is more dominant than the other? Strain hardening is more dominant than the relaxation. Right? By the time I come to the second stage, strain hardening and relaxation, they are going equally. If in the given time, 10 dislocations are obstructed, in the same time, some other 10 dislocations are relaxed. It's not necessarily the same dislocation which is obstructed will be relaxed. The number of dislocations which are flowing, which are slipping, will be the same. And it remains same. So whatever has got obstructed, the same number or same kind of a dislocation get relaxed somewhere else. And the material and deformation goes on at the same rate. By the time I reach the third stage, the flow of the material has taken place to such an extent that the formation of wide spaces at the grain junctions, grain boundaries. Therefore, any cross-sectional area effectively is reduced. Just like in necking, it can also be damaged to such an extent there could be nicks formed in the specimen. And then the applied stress is no more a constant value, it becomes concentrated at those local regions where the area of cross-section is reduced. So now deformation will get localized. More stress, more strain. And the area of cross-section reduces because of more strain, stress becomes more, so more strain. That is how the rate keeps on increasing with increasing time till the material fails or there is breaking taking place, splits into two or more parts. Okay? And this the curve which I am showing, this first one, which is at a lower level of stress or let us say lower temperature. First stage is very long and second stage begins after some time and it's going to be another very long stage. Tertiary stage will start after a very, very long time. But when the stress and the temperature become high or stress or the temperature become high, I probably see only the third stage. First stage, second stage gets localized right there. It's a very small time in which the first stage and second stage is completed. That is, the process of creep is very, very fast, such a high temperature, right? So that's the kind of thing which we observe. But the time scale depends upon the applied stress and the temperature. The time scale for the whole curve to be seen. In the low temperature, lower stress, the time may be much larger. But in a high stress, high temperature, the same thing is reduced to a smaller time. Right? So that is thus time is taken care of in that manner. Now let's look at those relaxation mechanisms, what we refer to the creep mechanism. Some of these things you have already seen. Cross slip of a screw dislocation. It doesn't require temperature. It doesn't require the help of, though the slip motion, the dislocation is itself a thermally activated process, depends upon the temperature. But if it is a screw dislocation which is obstructed, it can begin to cross slip over another slip plane. Only thing is I have to apply enough stress so that there is a resolved shear stress good enough on that slip plane for it to slip there. Resolved shear stress required should be critical value on the second plane where it is going to cross slip. This happens at low temperatures. It happens at low temperatures, but I need enough resolved shear stress. It should be critical value on the second. When there is an anti-dislocation which is obstructed, it has to change the slip plane from there. It can only climb, either climb up or climb down. It requires diffusion of atoms or the diffusion of vacancies, either towards the edge of the part plane or away from the edge of the part plane. Therefore, this requires elevated temperature. But stress can be low.
But how will climbing can cause a creep?
Climbing. See a dislocation which is moving here on this plane is obstructed right here. If it moves from here, goes over to this plane, there may not be any obstruction, it has jumped up and then it will start slipping there. The obstruction is here. Another obstruction, another strain field. Some strain field which is obstructing it here may not be present a few planes away, 5 planes away. So it can jump up by 5 planes and then start slipping. Or it can jump down by 5 planes and then start slipping. Right? So that's what is the climb, and that high temperature is required because diffusion is required. Diffusion is going to be faster, the temperature is higher. Alright? Let's look at the diffusional creep. This diffusional creep is also going to take place by diffusion of atoms or diffusion of vacancies. Okay? Let's say this is the force which you applied or the stress you applied, and this is the material which is deforming. In this case, vacancies have to move from these planes which are here perpendicular to the applied stress and go over to the planes which are parallel to the applied stress. And when that happens, what is going to happen is these layers will move inwards because vacancies have come. And atoms in the other direction have gone upwards and they have increased the atoms can come So area of cross section is reducing, length is increasing. Creep is going on, and deformation is going on, and this is a time dependent phenomenon. How many vacancies would have moved here depends upon the time, because the diffusion of vacancies. This is going through the lattice and is referred to as Nabar-Haring creep. The same thing can also be achieved in the material if the diffusion occurs along the grain boundaries. The polycrystalline solid. If the diffusion occurs along the grain boundaries, the effect is vacancies have to come to this layer. Vacancies have to come and this is to reduce. But this has to go through the grain boundaries rather than the lattice. That's called Hubble creep. So that's the diffusion along the grain boundaries, you know, is going to be easier. So that's lattice diffusion is going to be slower than the grain boundary diffusion. But the area of cross section available for the grain boundary diffusion is less. That's why it becomes more effective at lower temperatures. Right? So therefore, this is the two kinds of diffusion of vacancies. Is basically diffusion of vacancies, only the path used. In this case, it is a lattice which is used. In this case, it is the grain boundaries which is used. For diffusion, and the result is the area of cross section of specimen reduces and the length increases. So plastic strain is going on and material continues to deform. So creep goes on. Right. There is another mechanism which is also working. Well, before I talk about that, this diffusion creep is strongly temperature dependent. I should have very high temperature so that I can provide for diffusion of vacancies or diffusion of atoms. And applied stress need not be very high for this. Okay. Now there is another mechanism which also is working. It's called the grain boundary sliding. Let's see, in here I am showing the curve which I showed you earlier. The viscosity versus temperature, and that's the melting point. Well, for a crystalline solid, the viscosity, the liquid structure is small, but it increases with decreasing temperature. The melting point suddenly increases by 18 to 20 orders of magnitude, and then in the crystalline solid it increases slowly, gradually with decreasing temperature. But when it's glass-like structure, non-crystalline structure, the viscosity gradually increases, passes through a glass transition temperature, where the viscosity is 10 to the power 12 Pascal second, which we have defined arbitrarily as the dividing line between the solid and the liquid, and this is called the supercooled liquid. Here it is liquid, of course, and there it is glass. What happens for the non-crystalline solids? Now, in a solid, where I have grains like this, there is a region which is crystalline and is going to behave like the dotted line, and there is a region which is non-crystalline and is going to behave like this glassy material, non-crystalline structure. Which is the non-crystalline region, which is the crystalline region in a polycrystalline solid?
Along the grain boundary, is there
crystalline arrangement. It's a glossy matrix basically, and the grain boundaries are the the grains are the crystalline region, right? So here I have crystalline region, and here I have non-crystalline region, the grain boundaries. When I am at temperature which is above the 40% melting point, somewhere here below the melting point I am, at this temperature range, this is the viscosity of the crystalline solid, and this is the viscosity of the grain boundary region. And you apply the stress. The situation at this high temperature, elevated temperature, is like you have seen they are laying the carpet on the road. They bring the hot mix. Hot mix is pebbles which have been heated and coated with tar. That's called the hot mix. They lay it on the road and then they allow the road roller to move over this, stacks it, and they are all sliding. So this is the situation like that. We have a hot tar which is fluid and can flow. But inside pebble, though they are hot, they are very rigid. But those pebbles are able to slip one over the other and you can make a uniform carpet on the road. That's exactly what is happening here. Quite similar to that. That you have these regions which are glassy, or rather you can say it is not high temperature, then the supercooled liquid state. And when they applied stress, they start to slide against each other. Right? And because of the sliding taking place, deformation goes on. For here, I need high temperature so that the viscosity of the grain boundaries is very low. And secondly, I need high temperature because there should be a component of the applied stress which is the shear stress and can make the grain boundary slide. There could be a slip or the sliding motion taking place at the grain boundaries. Yes. Actual grain will not distort. There are no dislocations not taking part in this kind of a thing.
So then how is creep going on? Or creep is
Yeah, these grains when they slide, they get elongated in the direction of the applied stress. They start moving in the direction of the applied stress, no? So they start shrinking onto the lateral direction, and in the longitudinal direction they start extending.
will it be time dependent?
Yes. It's a viscous flow. Newton's law will work. Okay, it's a viscous flow because this is a viscous fluid basically, and it's not the viscosity is not very low that it will flow like water. Water has a very low viscosity, so it is under the applied stress only it is flowing. So I need both high temperature and high stress. For this phenomenon to take place. Now let's look at the materials where I can develop the resistance to creep. Alright, before I go over to this, I just now talked about the grain boundary sliding. Now tell me, if I have a fine grain material and I have a coarse grain material, where the grain boundary sliding would be more? In the fine grain, because there is more grain boundary area for the given volume of the solid. There will be more grain boundary sliding in the fine grain material. I said fine grain materials have better mechanical properties. Creep is at least the bad, worse. I need coarse grain material if I want to have effective creep. We'll talk about the resistance now. Shall see that. The resistance to creep, I must be able to stop these mechanisms which are working. Okay? That shall develop the resistance to creep. It is effective, the creep is effective, relaxation mechanisms are effective when temperature exceeds 40% of the melting point. So use the material, know its melting point, and use it below the 40% melting point. Where is the need for you to worry about the creep if you are using the material below 40% melting point? Engineers have a problem, serious problem. To get the efficiency in your carbon cycle, you have studied temperature of the source where you are operating should be high and temperature sink should be low. Right? And the efficiency of this cycle you have studied is T2 minus T1 by T2. What is the operating temperature is T2. T1 is the sink where the heat is exhausted. Okay, that could be room temperature or could be higher than the room temperature. Particularly in turbines, there are different stages. First stage T1 may be high, maybe 600-700 degrees centigrade. Second stage it may be less. Third stage may be still less, and so on and so forth. The starting temperature, initially the operation would be at high temperature like 1400-1500 degrees centigrade, where the efficiency should become high. If you have the T2 as 1400-1500 degrees centigrade, the efficiency would be more. You like to have a turbine not working less than 70% efficiency, right? So therefore you need the temperature to be high. Then try to find a material which has a high melting point. If I am working at 1500 degrees centigrade, which means about 1800 Kelvin, how much should be the temperature? 4500 Kelvin? 4500 Kelvin means more than 4000 degrees centigrade should be the melting point. Difficult to get a material. Tungsten is 3410 degrees centigrade, right? But then if I make any object out of tungsten, I have to melt tungsten first. Where would I keep it? The molten metal. I must have a container which has a melting point more than that. It's very difficult to form objects from tungsten. So we use normally a powder metallurgy route for making objects from tungsten. As a result, we have to live with materials with lower melting points than 3000 degrees centigrade. And most of them are either rarely found elements, if they are in the range of metals and alloys, or they are oxides. The problem with oxides which are available and I can make objects out of them, they cannot be used for structural application. They cannot be used for structural application because they are very brittle materials. Also, there are oxides could be acidic or could be basic in nature. So if I am using them somewhere where the medium is going to be acidic and I am using a basic lining, it will not work like in a reactor. All chemical engineers are used to using reactors at high temperature. Still they don't withstand the temperature, but you put a lining inside which acts as an insulator for the steel casing outside. At the same time, it can work at higher temperature. So there these oxides, the bricks which we use, magnesium oxide or iron oxide, these bricks or silica bricks, they are brittle and can be used under compression. So therefore I can use for lining. Only thing I have to ensure that what is the reactants and the products, if they are acidic, the lining should also be acidic in nature. So it doesn't corrodes or erodes with time in a faster manner, right? So that's the problem of temperature. I have to use the materials at high temperature. And I need the structural materials which can withstand the some ductility, some deformation. I am to restrict myself to first long period where I have iron, nickel and cobalt. These are the base metals which we use for materials at which are for creep resistant materials. All three of them have the melting points around 1500 degrees centigrade. It's good enough temperature, we have to live with it, but then we try to see now, can we improve their creep resistance further, other than the temperature. Temperature I have no control over now. So therefore, I have to see other mechanisms. The mechanisms which increase the strength we talked about is the strain hardening. Will it work? Why? 40% of the temperature is also the recrystallization temperature. 40% is melting point. So whatever effect you got by dislocation density, recrystallization will overcome that effect and it will be a very soft material. It will not be effective at all. So I cannot use that. Can I do the grain refinement? No. I cannot use the grain refinement? No. Because there will be grain boundary sliding. However, I can have a single crystal, yes. By making the single crystal, if I have to make a turbine blade, if you have ever seen this shape of a turbine blade, very complicated shape. But in the laboratory, they have made a small turbine with titanium single crystal blades. And below its melting point around 1600 degrees centigrade, for years it has worked. It is not shown the creep. So it's possible to use single crystals. Growing single crystals is very difficult. If so, then try to see that there is no grain boundary sliding. Grain boundaries are present but they don't slide. It's possible if you know where the force or the stress is coming. If force is coming in this direction, align the grain boundaries perpendicular to the force. And they will not slide. Right. This is called a bamboo structure. You have to develop it by crystal growing. But more serious problem is there is no single direction of force in the material when I am using it, whether it's a turbine or any other application. Force can come in any direction. So not very effective. Right? But this can also work. Try, attempts have been made in the bamboo structure. It doesn't slide. That doesn't show the creep. Right. So,
is it easy to arrange the grain boundaries in one direction only?
well, it's possible. It's possible you can do that. You have to put the nucleation sites such that they go parallel to each other. You have to do that.
So inclusion of other field particles is also helpful. They will also restrict the grain boundary movement.
The operating grain boundary themselves interface. Okay, I'll talk about those precipitate particles also.
So, but we have other mechanisms also other than this grain boundary, even crystals sliding along the grain boundary.
There are other things also. I'm just talking about the grain size effect because grain will affect only the grain boundary sliding. Grain boundary, if it is present, is going to affect only grain boundary sliding, nothing else. That's why I'm discussing that. You must understand why I'm discussing it. Grain is going to control only the mechanism of grain boundary sliding. Okay? Now if the solution is present, solute is present, it will provide the stream around the solute like it is providing at room temperature, it's providing a high temperature also. So it shall keep interacting with the moving dislocation to be very effective. As a matter of fact, some of the superalloys they call superalloys because they can resist creep. Development took some time, like 25 years, and having 10 to 25 solutes. But they should go in solution, that's important. Something is added just 0.2%, something is added 0.5%, something is added 1.5%, whatever can go in solution. And they will all resist. Some superalloys have the compositions like that. They have large number of alloying additions made. But all, huh?
What is the property that
They will stop the motion, the slip motion, the dislocation, obstruct, because they continue to provide the strain field around the solute. Whether temperature is low, temperature is high. If the matrix is expanding with temperature, bond length is increasing, it will increase for the solute also. The strain around the solute should continue to be there at all temperatures. So it will be effective. Right? The last one, I think we talked about the precipitation hardening. precipitation hardening will not work. Why? Temperature is so high that coarsening, or what we call overaging, will be very fast. However, it can be effective if there is no coarsening. Coarsening would not take place if there is no driving force for coarsening. And what is the driving force? Energy of the interface between the precipitate and the matrix. Well, they have developed some superalloys which provide the precipitate Ni3Ti or Ni3Al. Both are soluble in each other, and therefore I can write this as Ni3TiAl. This precipitate in the nickel matrix provides an interfacial energy of the order of 0.005 joule per square meter, much less than that of even the twin boundary. It's much less than that. So the driving force is not there, and it will continue to provide the creep resistance. Some of the superalloys are doing that, nickel-based superalloys. And second is the mechanism of coarsening. Particle, the solute has to go back into the matrix, and that solute atoms have to go and deposit on the neighboring particle which is going, like this. And these have to dissolve back into the matrix. If it is insoluble in the matrix, it will not be able to dissolve. It will not be able to go and deposit there. But if it is insoluble, how did it come out as a precipitate? Then it is not a precipitate. Then it is a dispersed particle, what we call the dispersion hardening. Solid particles, fine powder, very fine powder, like the size of 200 angstrom, as I said, we, in the form of that powder, we mix it with the molten metal and then solidify it. Right? One example of this is thorium dioxide, which we call thoria dispersed nickel. In the market, commercially it is called TD nickel. And then the other alloys, which are called the SAP alloys, sintered aluminum products. Sintered aluminum products. What happens here is, we know that aluminum is very reactive material. There is aluminum oxide formed on each aluminum particle. When I sinter such a material, the diffusion causes the Al2O3 to move from the surface and cluster here at the junctions. Like this, alumina gets deposited, and then aluminum can diffuse like this and the bond can form. This is a powder metallurgy technique. Alumina is not soluble in aluminum matrix, and this provides the dispersion hardening. Right? Okay, we shall